A star is gone, not exploded, not fading slowly over millions of years the way stars are supposed to die. Gone, just gone. One image it was there, the next image it was not. And the telescope that caught this, the most powerful sky-watching machine ever built, has only just started looking up. If you have ever looked at the night sky and felt like something massive is out there waiting to be found, you are right. And right now, we are finding it. Subscribe if you want to know what is actually happening in space, because the next few years are going to be unlike anything in the history of astronomy. Let us talk about what just happened. There's a telescope sitting on a mountain in Chile called the Vera C. Rubin Observatory. It sits at 8,800 feet above sea level on a peak called Cerro Pachon, where the air is thin, dry, and dark enough to see the universe with almost no interference from city lights or moisture. Scientists have been building this thing for over 2 decades. The planning started before most people had smartphones. And in June 2026, just weeks ago, it officially opened its eye on the universe and began a project called the Legacy Survey of Space and Time. The LSST, 10 years, every night, the entire southern sky. To understand why this is such a big deal, you need to understand what this camera actually is. The Rubin Observatory is equipped with the largest digital camera ever built by human beings. It is a 3,200 megapixel camera. For context, the best smartphone camera you can buy right now is around 200 megapixels. The Rubin camera is 3,200. One single image from this camera is so enormous that you would need hundreds of ultra-high definition TV screens side by side just to display it at full resolution. The telescope itself has an 8.4 meter mirror. It can detect objects so faint they are 100 times dimmer than anything previous sky surveys could pick up. And it does not just take one picture a night and call it done. It takes a new full sky image approximately every 40 seconds, every single clear night for a decade. What this creates is not a photograph of the universe. It is a movie, a 10-year ultra-high definition time-lapse movie of the entire sky. Every star, every galaxy, every rock floating through space, every explosion, every appearance, and every disappearance. All of it recorded, cataloged, and studied. Scientists have been waiting for this for 20 years, and now it is running. So here is where the star disappearance comes in. In February 2026, just a few months before the full survey officially launched, a team of astronomers published a paper in the journal Science that stopped the entire astronomy world in its tracks. They had found a star in the Andromeda Galaxy, our nearest galactic neighbor, sitting about 2.5 million light years away, that had simply vanished. The star is called M31 2014 DS1. That name tells you it was in Messier 31, which is the Andromeda Galaxy, and it was first flagged as unusual back in 2014. It was a yellow supergiant. Massive, bright, one of the most luminous stars in the entire Andromeda Galaxy. The kind of star that, if it were in our galaxy, would be visible to the naked eye from Earth, even during the day. The kind of star astronomers know well and track regularly. Then it started doing something strange. In 2014, it began to brighten in infrared light. Not in the kind of way that signals an explosion is coming, more like a slow warming, a buildup. Astronomers who study dying stars recognize this pattern as something that can happen when a massive star near the end of its life begins losing its outer layers, throwing material off into the space around it. The dust from that ejected material can glow in infrared. So scientists noted it, filed it away, and kept watching. Then between 2016 and 2019, the star collapsed in brightness. Not slowly, not over thousands of years. In 3 years, its visible light faded by a factor of 100. 100 times dimmer in 3 years. By 2022, the star had essentially vanished from near-infrared observations entirely. By 2023, it was completely undetectable from the ground in optical wavelengths. It was just gone. Lead researcher Kishle Day, an astrophysicist at Columbia University, found this hiding in public archival data. Data from NASA's NEOWISE mission, an infrared telescope that had been mapping the sky from 2009 to 2024. He described his reaction when he first saw the data. He said, and this is a real quote, "I got goosebumps when I saw it disappearing into darkness." His team named it M31 2014 DS1. And he said, "This star used to be one of the most luminous stars in the Andromeda Galaxy, and now it was nowhere to be seen." Imagine if the star Betelgeuse suddenly disappeared. Everybody would lose their minds. The same kind of thing was happening with this star. The evidence pointed to something that astronomers had theorized for decades, but had never had a clear, confirmed observation of: a failed supernova. You need to know what a failed supernova is, because it is one of the most dramatic things in the universe, and it happens without making much noise at all. When a massive star dies, the textbook version goes like this. The core, which has been fusing lighter elements into heavier ones for millions of years, finally runs out of things to fuse. It collapses under its own gravity in a fraction of a second. That collapse sends a shockwave ripping outward through the star. The shockwave is powerful enough to blast the outer shell into space at incredible speeds. That blast is the supernova. It shines so bright that for a few weeks it can outshine the entire galaxy it lives in. But theory has long predicted that for some massive stars, something different happens. The shockwave is not strong enough. Instead of escaping outward, the shock stalls. The outer layers fall back down. The core, which was trying to become a neutron star, accumulates so much falling material that it crosses a threshold. And instead of a neutron star, it becomes a black hole. Directly, quietly, without the grand explosion. The star does not go out in a blaze. It just goes out. This is called a failed supernova. The theory says it should happen. The math supports it. But actually, watching one in real time has been almost impossible, because the defining feature of a failed supernova is that nothing happens. You cannot watch for an explosion because there is no explosion. You have to watch for a disappearance, and watching for something to disappear requires that you are watching it before it disappeared. This is exactly what makes Rubin such a game changer. Before Rubin, catching a failed supernova was like trying to notice one candle quietly going out in a city of 1 billion candles. With Rubin, you have a camera recording every candle, every night, for 10 years. The team that found M31 2014 DS1 was piecing together a timeline from different telescopes and observation programs. It took years of forensic work to confirm what had happened. There is still debate. In July 2026, astrophysicist Noam Soker published a challenge to the failed supernova interpretation, arguing the data could also be explained by a violent binary star interaction followed by heavy dust formation. He does not rule out a black hole entirely, but argues the quiet collapse model requires very specific conditions hard to reconcile with what JWST currently sees at the site. The question is still open, but whether M31 2014 DS1 becomes the definitive confirmed failed supernova or not, we know these events happen, we know what they look like, and we need to catch more of them. That is exactly what Rubin was designed to do. On February 24th, 2026, the Rubin Observatory ran a test of its alert system. This was before the full survey officially launched. Scientists pointed the telescope at a patch of sky for which they already had comparison images from previous surveys, and they let the camera run. In a single night, the system flagged 800,000 alerts, 800,000 separate events in the sky that had changed, appeared, or disappeared compared to the previous images. Stephen Smart, who is a researcher at the University of Oxford and serves as scientific lead for one of the 7 data broker networks connected to Rubin, described it this way. He said everything that changed, appeared, or disappeared was cataloged and triggered an alert. All of it automatically, within seconds of the images being captured. Among those first 800,000 alerts were detections of supernovae in distant galaxies, variable stars pulsing and shifting in brightness, active galactic nuclei, the engines at the center of galaxies, powered by supermassive black holes, and dozens of previously unknown asteroids moving through our own solar system. All from one night of testing. And see, the full survey reached operational speed. That 800,000 number was expected to grow to 7 million alerts per night, every single night. 7 million separate cosmic events flagged and sent to scientists and brokers around the world so that follow-up observations could begin within minutes. 7 million per night for 10 years. Smart, who is specifically focused on finding failed supernovae with Rubin, noted that the telescope goes 100 times fainter than other sky surveys. That depth matters because stars disappearing quietly are by definition dim events. There is no bright explosion to catch. The star just gets fainter and fainter until it is gone. Only a telescope capable of detecting incredibly faint sources and watching the same patch of sky over and over and over across years has a real chance of catching the full arc of a disappearance in progress. And while all of that was being set up, something else happened, something equally dramatic. In March 2026, a space telescope called the Einstein Probe, an X-ray observatory operated by a collaboration of European, Chinese, and German space agencies, caught a brief flash of soft X-ray radiation from a galaxy about 500 million light-years away. Within an hour, ground-based telescopes around the world began pointing at the same spot. What they found was a supernova, but not just any supernova. This one, designated SN 2026GZF, had been caught at the very first moment of its explosion. The X-ray flash was the shock breakout, the moment when the shock wave from a collapsing stellar core slams into the outer surface of the star and erupts into space for the first time. This is technically the very beginning of every supernova, but it lasts only minutes and has to be caught essentially by chance. This one was the faintest shock breakout ever recorded. Rubin played a direct role. The supernova occurred in what is called the Cosmos Deep Drilling Field. a patch of sky Rubin had been repeatedly photographing during its commissioning work in 2025 and early 2026. That archival data, released publicly as part of Rubin's early data preview 2, allowed astronomers to look back and see the star as it existed before it exploded. They could point to a blue dot in a photograph taken months earlier and say, "That is the star that just died." Astronomer Jillian Rastinajad at the University of Maryland described what the multi-telescope campaign revealed. They were able to map out the structure of the material surrounding the star and understand its violent lifestyle before collapse. The star was confirmed to be a Wolf-Rayet star, a massive hot star that had shed most of its outer hydrogen layer before death. The supernova was a broadline type Ike, among the most energetic stellar explosions in the universe, yet no relativistic jets were detected, and the shock breakout was unusually faint. The star died powerfully, but without some of the hallmarks expected for this class of event. What this showed is exactly the kind of science Rubin was built for. The archival images meant scientists already had a photograph of the star before the crime was committed. The real-time alert infrastructure meant that the moment something changed, the right people were notified fast enough to catch everything before the evidence faded. Let us zoom back out, because this is important. Before Rubin, watching the sky change was hard. Telescopes are powerful but narrow. Catching a transient event, something that happens fast and then is gone, required either incredible luck or very fast response times. You might know a supernova happened, but unless you had a camera at that exact spot at the exact right moment, you missed the beginning. You only saw the aftermath. Piecing together what happened was always partly guesswork. Rubin fundamentally changes this. Because it watches the entire southern sky every few nights, it is not missing anything in its field of view. Every object that changes brightness is caught. Every object that appears is cataloged. Every disappearance is flagged. The system generates comparison images automatically, subtracting the known background and highlighting only what changed, and it sends alerts within 60 seconds of each image being processed. This is not a small upgrade from what came before. It is a completely different mode of doing astronomy. The Zwicky Transient Facility in California, one of the previous leaders in time domain astronomy, generates roughly 1 million alerts per night at its peak. Rubin at full speed will generate 7 million per night. The full 10-year dataset will contain measurements of billions of objects with trillions of individual data points, the largest astronomical dataset ever assembled by a single project in human history. So what is Rubin actually looking for, beyond stars disappearing? The core scientific goals are enormous. Dark energy and dark matter top the list. About 95% of the universe is made of these two things, and we do not understand either of them. We cannot see dark matter directly. We know it exists because of the way it affects the movement and structure of galaxies. The first person to provide convincing evidence for dark matter was the astronomer this telescope is named after, Vera Rubin. She spent years in the mid-20th century studying how galaxies rotate, and she found that they spin in ways that are impossible unless there is a huge amount of invisible mass holding them together. Her work was revolutionary and initially dismissed by parts of the astronomy community. The telescope named after her is now one of the primary instruments humanity has for understanding the very thing she discovered. By mapping the shapes and positions of billions of distant galaxies with extraordinary precision, Rubin will detect the subtle distortions dark matter creates in space. It will also track how those distortions change over time, which will help scientists understand dark energy, the force accelerating the expansion of the universe. Beyond that, Rubin is also the most powerful solar system discovery machine ever built. In just its first month and a half of early optimization surveys before the full LSST officially began, Rubin had already found over 11,000 previously unknown asteroids. 33 were near-Earth objects. 380 were trans-Neptunian objects, rocks drifting in the outer solar system beyond Neptune, all from just the warm-up period. And then there are the things nobody has a name for yet, new classes of events that do not match any existing category. Every major telescope in history has found things it was not specifically looking for. Rubin, by watching more of the sky with more depth and more frequency than anything before it, will almost certainly find things that rewrite textbooks in ways nobody can predict right now. There is one more thing worth saying about the star that disappeared. M31 2014 DS1 is still a mystery in the most productive sense. Scientists are still arguing about what exactly happened to it. JWST has been pointed at the site and has detected a faint infrared source at the location, which some researchers interpret as evidence of fallback accretion onto a newly formed black hole. Others, like Soker, argue this fits better with dust formation after a binary star merger. The debate is not settled, but this is exactly how science is supposed to work. An observation so unusual that it forces everyone to argue, test, and think harder. And the key thing is that now, with Rubin running and generating millions of alerts per night, The era of missing these events is over. If another star in a nearby galaxy begins the pattern of infrared brightening followed by optical fading, Rubin will catch it. Not after the fact from archival data, not pieced together from instruments that were pointed in that direction by coincidence, but in real time as it happens, with immediate alerts going to dozens of research teams worldwide. The first confirmed failed supernova, unambiguous and real-time observed from start to finish, is probably in the data being collected right now. Somewhere in the southern sky tonight, some massive star is in the late stages of a core that is about to give out. The shockwave will stall. The outer layers will fall back. The light will fade over months or years. And unlike every star that has ever done this before in the history of the universe, this time, a 3,200 megapixel camera watching every 40 seconds will be there for the whole thing. We are at the beginning of a new era, not just in astronomy, in our relationship with the universe itself. For the first time, we have a machine capable of watching everything that changes in the night sky, at the same time, continuously, for a decade. The sky is not a static backdrop anymore. It is a living document being written and rewritten every night, and for the first time, we are reading it fast enough to actually understand it. A star disappeared. Right now, we know what happened. And because of what just came online in Chile, next time it happens, we will watch it happen in real time from the very first moment. That is where we are. That is what is happening. And this is only the beginning of what Rubin is going to find. And to really understand why this moment matters, you have to think about the problem Rubin is solving, a problem that has haunted astronomy for a long time. Stars vanish. We know they do. But historically, the evidence has been gathered the hard way. You take a photograph of a patch of sky in 1950, you take another photograph of the same patch in 2020, you compare them carefully, and sometimes where there was once a bright dot, there is now nothing. That is how many discoveries of vanishing objects have been made. Comparing old photographic plates to modern digital sky surveys, looking for things that were once there and are now gone. The process is slow, imprecise, and heavily dependent on what instruments happen to be pointed where. The problem is obvious once you see it. If a star disappears slowly over a decade and your two comparison images are 70 years apart, you missed the entire story. You just see the ending. The star was there. Now it is not. What happened in between? You have no idea. Was it a failed supernova, a stellar merger, a star obscured by a massive dusty shell? You cannot know from two snapshots. Rubin solves this completely. Instead of two snapshots separated by decades, you have thousands of images of the same spot separated by days, stretching across a decade. You do not just know a star disappeared, you know exactly when the brightness started changing. You know the precise rate at which it faded, you know which wavelengths dimmed first. You can watch the entire life cycle of the event. And because the alert system is real-time, you can point other telescopes at the exact spot while it is still happening, not years after the fact. Smart at Oxford said it plainly. Rubin goes 100 times fainter than other sky surveys. That depth means catching the event even when the star's light has dropped to a tiny fraction of its original output. A failed supernova does not blink off instantly. It dims, slowly at first, then faster. Only a telescope sensitive enough to follow it all the way to its faintest readings can confirm the star actually vanished rather than just got dimmer. The discovery of M31 2014 DS1 also carries a lesson about how big data changes science. Keisha Day was going through archival infrared data from NEOWISE systematically, not looking at one star carefully, looking at millions of stars automatically, searching for patterns. The evidence of the star's disappearance had been sitting in public archival data for years and nobody noticed. It took an algorithmic search across a massive dataset to pull the signal out. This is the future of astronomy. Not a single scientist at an eyepiece noticing something odd. Machine learning algorithms processing hundreds of terabytes per night, flagging anomalies, presenting the most interesting ones to human researchers who decide where to point follow-up instruments. The human remains essential for the final call. But the initial discovery layer is automated by necessity. Rubin generates 20 terabytes of raw data per night, every night, for 10 years. No human team could process that manually. 7 data broker networks connected to Rubin exist to handle this flood. Each broker applies different filters looking for different kinds of events. The same raw data flows through all of them simultaneously, and each returns its own prioritized list of interesting events to different scientific teams worldwide. Scientists subscribe to the kinds of alerts they care about. A team hunting failed supernovae sets their filters for long timescale fading in massive stars within a certain distance. When those criteria are met, they get an alert. They check it. They request follow-up time on bigger telescopes. Within hours, the world's best instruments can be looking at the same object. Rubin is committed to making all alerts publicly available to anyone. Citizen scientists, students, amateur astronomers, all accessing the same streams that professionals use. In the first year of the full LSST, Rubin is expected to photograph more objects than all other optical observatories in human history combined. There is something worth sitting with here, beyond the technical details. The star M31 2014 DS1 died somewhere around 2.5 million years ago. The light showing us its disappearance has been traveling through space since before modern humans existed. Those photons left a dying star at a time when our ancestors had no concept of stars at all. The universe does not know we are watching. It does not arrange itself for our benefit. But we are watching now in a way we never have before. Rubin is not just a bigger telescope. It is a fundamentally different relationship between human beings and the cosmos. We have gone from painting static portraits of the sky to filming a continuous, living documentary every night for a decade, missing nothing. The great questions: what the universe is made of, how stars live and die, what happens when the largest suns run out of fuel and collapse. These will not be answered by one dramatic observation. They will be answered by a decade of patient, relentless, automated watching, by 7 million alerts per night, by evidence so overwhelming that arguments which took decades before will be settled in months. M31 2014 DS1 may or may not get its final chapter written this year. The debate is still running. JWST is still observing the site. New papers keep coming. But whether that specific star's story is resolved in 2026 or 2027, the bigger story is clear. Stars disappear without exploding. Black holes form quietly. The universe has been doing this for 13 billion years without us catching it clearly. Now we have a camera that will catch it, frame by frame, in real time as it happens. Tonight, under the dark skies of the Chilean Andes, the 3200 megapixel camera of the Vera Rubin Observatory is taking a new image of the southern sky. In 40 seconds, it will take another. Somewhere in those images, something is changing. Something that was there before is getting dimmer and dimmer and dimmer. This time, we will see it. And it just turned on.